I have always been fascinated to understand intuitively how a new branch of mathematics came into existence. Today I'm going to discuss about vectors. Before vectors, mathematicians and physicists worked almost entirely with scalars, single numbers that carry magnitude only. For centuries this was enough, because most of early science asked how much. But by the 17th to 18th century, a different kind of question kept showing up, one that plain numbers simply could not answer. How much, in which direction? Consider a ship being pushed by wind from the northeast, while a current pulls it east. A sailor doesn't just want to know the total force as one number. A single number can't tell you where the ship will actually end up. You need magnitude and direction combined into one mathematical object that can be added, scaled, and combined the way forces, velocities, and displacements actually combine in nature. This is the core reason vectors were invented. The real world contains quantities that have direction, and scalar arithmetic has no way to represent or combine direction. The historical trail. Galileo studied projectile motion and realized that horizontal and vertical motion had to be treated separately and then combined, an early, informal glimpse that motion isn't one number. Newton built on this in the Principia, published in 1687, where his treatment of combined forces used a geometric method called the parallelogram of forces. If two forces act on an object, you draw them as two sides of a parallelogram, and the diagonal gives the combined, resultant force. Caspar Wessel, Jean-Robert Argand, and Gauss represented complex numbers as points and arrows in a plane. This arrow idea planted the seed of vectors. They also found something else. Multiplying two of these arrows together composes their rotations. Multiply by a unit arrow, and you simply turn the original arrow by an angle. Let's first understand the problem Hamilton was solving. Complex numbers of the form of plus bi let you represent points and rotations in a 2D plane, and multiplying two complex numbers elegantly combines rotations. Hamilton wanted the same trick for 3D, some kind of number system where multiplying two of these numbers would compose 3D rotations the way complex number multiplication composes 2D rotations. He first tried triplets, numbers of the form of plus b I plus cj, with three components. This should work for representing a point in 3D, but it broke down badly when he tried to multiply two of them. He spent about 13 years failing to make triplet multiplication behave consistently. He suddenly realized the fix wasn't adding one more dimension in the same way. It was needing a fourth component of a fundamentally different character. Q equals W plus X, I plus Y, J plus ZK, where I, J, K are three separate imaginary units, with rules like I squared equals J squared equals K squared equals I, J, K equals -1. In a famous moment on October 16th, 1843, walking along the Royal Canal in Dublin, he had the insight that he needed four components, not three, and carved the fundamental formula for quaternions into the stone of Broom Bridge on the spot. Once he had this four-component object, he noticed it naturally split into two pieces that behave completely differently when you multiply two quaternions together. The W part, a plain real number, which he called the scalar part, and the X, Y, Z part, three components that transform together, rotate together, and behave exactly like a directed quantity in 3D space, which he named the vector part. This emerged because when you multiply two quaternions, the math produces an output that separates into a scalar term that looks exactly like negative a dot b, our modern dot product, and a three-component term that looks exactly like a cross b, our modern cross product. In other words, the dot product and cross product were literally hiding inside quaternion multiplication before anyone had to find them separately. Josiah Willard Gibbs and Oliver Heaviside were physicists and engineers frustrated that Hamilton's quaternions were unnecessarily complicated for the actual physics problems they faced, especially applying Maxwell's equations, which describe electric and magnetic fields and are fundamentally about vector fields in 3D space. Independently, in the early 1880s, they each essentially took quaternions, discarded the scalar part and the unnecessary 4D structure, and kept just the useful 3D vector part, formalizing vector addition, the dot product, and the cross product largely as we teach them today. So vectors were not invented for elegance. They were reverse engineered from necessity. Vectors went almost completely for the things Gibbs and Heaviside built them for: general physics, mechanics, electromagnetism, force, velocity, and field problems. But quaternions came roaring back for one specific job, representing 3D rotations, spacecraft and aircraft attitude control, computer graphics, game engines, robotics, VR, and AR. Representing a 3D rotation with 3 numbers suffers from gimbal lock, where you can lose a degree of freedom at certain orientations. Quaternions represent rotation with 4 numbers and avoid gimbal lock entirely. Vectors and quaternions didn't end up as competitors. They ended up specializing. Let's get back to understanding vectors. This is the single most important conceptual hurdle, so let's slow down here. When you multiply 2 regular numbers, say 3 times 4 equals 12, you're scaling one quantity by another along the same single line, the number line. There's only one kind of information involved: magnitude. Multiplication is well defined because there's nowhere else for the meaning of the operation to go. A vector isn't one piece of information. It's 2 bundled together: magnitude and direction. Now ask, what should multiplying 2 vectors mean? If you tried to multiply component by component, like scalars, you'd get a result, but it wouldn't correspond to anything physically meaningful. A valid vector operation must give the same physical answer regardless of which coordinate system you use to describe it. Component-wise multiplication fails this test. It is not coordinate-free, so it can't represent anything real. The dot product, a dot B equals magnitude times magnitude B times cosine theta, which also equals a xbx plus a yby plus a zbz. The output is a scalar, not a vector. The meaning is projection, how much of one vector lies along the direction of the other. Watch the angle change. The shadow of onto shrinks as theta grows, hits 0 at 90 degrees, and flips negative past that. Example: work done by a force, W equals F dot D. If you push a box with force at an angle, only the component of force along the direction of motion actually does work. As the box slides, the work meter fills up proportionally to F dot D. Now replay at 90 degrees. Force straight up, box still slides horizontally. The box slides, but the work meter stays flat at 0. Exerting force does not mean doing work. Plain multiplication could never capture that. The dot product can, because it inherently accounts for the angle between the two. The cross product. A cross B equals magnitude A times magnitude B times sine theta times n hat. The output is a vector perpendicular to both original vectors. The meaning is a new axis or direction generated by the twisting relationship between the 2 inputs. The right-hand rule tells you which way it points. Curl your fingers from toward B, and your thumb points along the result. Example: torque, the twisting force on a wrench. Tau equals or cross F. The direction a bolt turns depends not just on how hard you push, but on the geometric relationship between the wrench's arm and the direction of your push. Torque pops out perpendicular to the wrench's plane, and the bolt begins to turn. Now, push straight along the wrench's arm instead. Force parallel to R. The torque vector shrinks to zero length. No twist, no torque. That new direction popping out is something ordinary multiplication has no concept of at all. Ordinary multiplication only has to preserve one kind of information: size. Vector multiplication has to decide what happens to direction 2, and there are two genuinely different, physically meaningful answers, so mathematics gave us both, each for a different real-world question. The decision comes down to what kind of answer the question is asking for. Ask, am I looking for a single number, or am I looking for a new direction? Use the dot product when a question is about overlap, alignment, or projection. Signal phrases like how much of X acts along Y, how similar, how aligned. Use the cross product when the question is about generating a new axis, rotation, or perpendicular effect. Signal phrases like twisting, rotation, perpendicular to both. Everything up to now, addition, dot product, cross product, is vector algebra. Operations on vectors are fixed single arrows. That's the toolkit Gibbs and Heaviside pulled out of Quaternions. Vector calculus is the next layer up. It asks, what happens when a vector changes from point to point in space, or changes over time? Instead of one arrow, you now have a vector field, a vector value attached to every point in space. This is precisely why Gibbs and Heaviside were doing this work in the first place. Maxwell's equations, the four equations that describe all of electromagnetism, are entirely vector calculus statements about the electric and magnetic fields as fields that fill space. You literally cannot state Maxwell's equations without gradient, divergence, and curl. Here's the hierarchy. Scalars, single numbers. Vectors, magnitude and direction, fixed in space. Scalar fields, a number at every point in space. Vector fields, a vector at every point in space. And vector calculus, the tools to analyze how scalar and vector fields change from point to point, gradient, divergence, and curl. Picture wind velocity at every point in the atmosphere, a vector field alive and flowing. The gradient measures which direction a scalar field increases fastest and how steep that increase is. Input, a scalar field. Output, a vector field. Del f equals the partial derivatives of f with respect to x, y, and z. Imagine a temperature map of a room or elevation on a hiking map. At any point, the gradient is an arrow pointing in the direction where the value increases most steeply, and its length tells you how steep that increases. Standing on a hillside, the gradient of the elevation function at your feet points directly uphill in the steepest direction. Water flows in exactly the opposite direction, downhill along the negative gradient. This is literally how gradient descent in machine learning works. To minimize a loss, the algorithm repeatedly steps in the negative gradient direction, downhill on the error surface. Let's work an example. F of x, y equals 100 minus x squared minus 2y squared. The gradient, term by term, is minus 2x minus 4y. Plug in the point 3, 2. Partial f over partial x is minus 2 times 3, minus 6. Partial f over partial y is minus 4 times 2, minus 8. So the gradient at 3, 2 is the vector minus 6, minus 8. Here, negative 6, negative 8 says, move negative 6 in the x direction and negative 8 in the y direction to go up. The magnitude, 10, tells you how steep. The sign tells you which way along each axis. Why the point 3, 2? Any point works. Here's the gradient reevaluated at 1, 1, minus 2, minus 4, Magnitude about 4.47. Visibly shorter. Closer to the peak, the slope is gentler. What is -6? -8 point back toward the origin. Look at it from above. For this symmetric bowl, contour lines are ellipses centered at the origin, and the gradient is always perpendicular to the local contour line, pointing toward higher elevation, back toward the peak. Here's that same 3, 2 with its contour ring, the gradient sitting exactly perpendicular to it. Its magnitude, square root of 36 plus 64, square root of 100, exactly 10. Normalize it, and the unit direction is -0.6, -0.8. Flip that, and walking in 0.6, 0.8, the opposite direction descends fastest. Same idea as the water droplet. Divergence measures whether a vector field is spreading outward from a point, like something is being created there, or collapsing inward, like something is being absorbed. Input, a vector field. Output, a scalar field. Del.f equals partial fx over partial x, plus partial fy over partial y, plus partial fz over partial z. Positive divergence, a tiny faucet, a source. Negative divergence, a tiny drain, a sink. Zero divergence, no net creation or loss, it just swirls. Zero divergence is one of Maxwell's equations. Del.B equals 0, meaning magnetic field lines never start or end. Follow the loops around a bar magnet. Out the North Pole, back in through the South continuously, forever. Gauss's law. Del.E equals rho over epsilon 0. Positive charges are literally sources of the electric field lines radiating outward. Negative charges are sinks, field lines converging inward. Same picture as before. A worked example. F of x, y, z equals x squared, 2y, negative z. Its divergence, term by term. 2x plus 2, minus 1, which simplifies to 2x plus 1. Evaluate at 1, 0, 0. 2 times 1 plus 1 equals 3. Positive, a source spraying outward. Evaluate at negative 1, 0, 0. 2 times negative 1 plus 1 equals negative 1. Negative, a weak sink pulling in. Contrast that with the pure rotation field. F equals y, negative x, 0, the same swirl we saw before. Its divergence, 0 plus 0 plus 0, 0, everywhere. Nothing created, it just swirls. Curl measures the tendency of a vector field to rotate or swirl around a point. Input, a vector field. Output, a vector field. Del cross F. Here's our swirl field again. Drop a tiny paddle wheel into it. If the field would spin the wheel, curl is non-zero. The curl vector points along the axis the wheel spins around by the right-hand rule. Exactly the same right-hand rule from the cross product. The magnitude tells you how fast it would spin. If the field flows past without spinning the wheel, curl is 0, irrotational. Drop the same wheel into a uniform field. It translates, but it never spins. The magnetic field circling a current-carrying wire has non-zero curl. Del cross B equals mu0 J. Wherever there's current, the magnetic field curls around it. Same right-hand rule. Thumb along the current, fingers curling in the direction of B. Type out the curl formula and substitute F equals Y. Negative x, 0, component by component. First component, 0 minus 0, 0. Second component, 0 minus 0, 0. Third component, negative 1 minus 1, negative 2. So curl F equals 0, 0, negative 2. Non-zero curl, pointing in the negative z direction. A paddle wheel dropped anywhere in this field spins around the z-axis by the right-hand rule. A curl of -2z hat means it spins clockwise when viewed from positive z looking down. The magnitude 2 tells you the spin rate. Contrast with the uniform field, f equals 1, 1, 0. Every partial derivative is 0, so curl is 0, 0, 0, irrotational, just like before. Are the del, operator, nabla just partial derivatives of vector functions? Yes, all three are built from partial derivatives. That's precisely what del is, a vector-like operator. Scalar times vector, scaling, morphs into the gradient. It turns a scalar field into a vector field. The dot product morphs into divergence. It turns a vector field into a scalar field. The cross product morphs into curl. It turns a vector field into a new vector field. There are exactly three operations because del behaves formally like a vector, and there are only three ways to combine a vector-like object with a field: scaling, dot product, cross product. In machine learning, every data point, a row in your data set, is literally a vector in n-dimensional space. Take a spreadsheet of customer purchases: electronics, groceries, apparel. Each row lifts off the page and becomes an arrow in three-dimensional space, one axis per column. Distance between customers, similarity between documents, cosine similarity, is literally the dot product, dressed up. Plot both purchase vectors. A equals 4, 1, 0 for customer A. B equals 3, 1, 1 for customer B. Their dot product. 4 times 3 plus 1 times 1 plus 0 times 1 equals 13. The magnitude of A is root 17, about 4.123. The magnitude of B is root 11, about 3.317. Cosine of theta equals 13, over 4.123 times 3.317, about 0.950. So theta is about 18.2 degrees. 18 degrees apart. These two customers shop almost identically. Both lean heavily electronics, light groceries, and apparel. Word embeddings take this even further. The words themselves become vectors. Plot king, man, woman, and queen in word vector space. King minus man is the royalty direction. Add that direction to woman, and it lands almost exactly on queen. King minus man plus woman approximately equals queen, literally vector addition. Computer graphics and game engines run on vector math constantly. Take something as simple as an object spinning in a scene. Under the hood, that rotation is tracked the same way Hamilton's Quaternions track it. Q equals W plus X, I plus Y, J plus CK. The camera itself is just another object with a position vector that changes over time. Its velocity is simply the rate that position vector is changing frame by frame. And when light hits a surface, the engine needs the surface's normal vector, perpendicular to the face, to work out reflection. The angle the light comes in at equals the angle it bounces back out, mirrored across that normal, landing in the viewer's eye. GPS navigation, bearing and distance, wind and ocean current forecasts, sports analytics. A football pass has a vector, speed and direction. A pilot's GPS reports the aircraft needs to reach a waypoint 120 kilometers east and 90 kilometers north of its current position. That displacement is a vector. D equals 120, 90 kilometers. Magnitude, the straight line distance. Draw the 120 kilometer east leg, then the 90 kilometer north leg, and the hypotenuse is D itself. Magnitude of D equals square root of 120 squared plus 90 squared equals square root of 22,500 equals 150 kilometers. Direction, the bearing, measured clockwise from north. theta equals atin 2 of 120, 90, about 53.1 degrees east of north. So the GPS instructs a course of roughly 053 for 150 kilometers. If wind then pushes the aircraft with its own vector, W equals -10, 5 kilometers over the next hour, the actual ground track displacement is the vector sum. D actual equals D plus W equals 110, 95. A new magnitude and a new bearing computed exactly like adding any two vectors. This is the same addition used earlier for combining forces, and the same reason a single number can't describe navigation. You need both how far and which way. A vector is best understood not as an arrow with a magnitude and direction, but as a member of a vector space. Any set of objects that can be added together and scaled while obeying consistent rules, associativity, distributivity, zero element, and so on. This reframing is powerful because it explains why vectors show up in places that have nothing to do with arrows in space. A list of stock returns is a vector. A polynomial is a vector in a vector space of polynomials. A grayscale image is a vector. Each pixel intensity is a coordinate. And a song's audio waveform, sampled at discrete points, is a vector too. Different objects, same underlying move. From a sailor needing direction to a bridge carved with a new kind of algebra, a shadow that measures alignment, a rule for the hand that finds perpendicular, a hill that points the steepest way up, a compass that finds you home, and numbers that were never really about arrows at all. Thank you.